So let's talk briefly about shape now, geometry. Now that we know all of that, we've seen that hybridization thing. Now we can determine the relative shapes of molecules. We have a couple of different options here. And the first thing that it's going to ask you is the steric number. Now, what is the steric number referring to? The steric number is really referring to the number of sigma bonds around a carbon. So if it's an sp3 hybridized carbon, it always has 4 sigma bonds around it, so its steric number is 4. If it's an sp2 hybridized carbon, it always has 3 sigma bonds around it, so its steric number is 3. If it's an sp hybridized carbon, its steric number is 2. Right? And the way you can think about that is the steric number is the number of s and p orbitals combined to make the sp hybrids. So sp3, 1s, 3p, 1s plus 3p is equal to 4 hybrid orbitals. 1s plus 2p is equal to 3 hybrid orbitals. 1s plus 1p is equal to 2 hybrid orbitals. Steric number is equal to that number of sp hybrid orbitals. And that's just saying that for every hybrid orbital, you have one group of electrons that's going to try to push away from any other groups of electrons as far as possible. So if you have 4 steric groups, you're going to push all those 4 away from each other as far as possible. And that's going to amount to 109.5 degree bond angle. That's going to give you this shape that we call tetrahedral, right? And I called that one out on the sp3 hybridized slide. If one of those steric groups is a lone pair, so lone pairs count, by the way. Lone pairs count in your shaping. So here, if this is a nitrogen, right, say this is a nitrogen, NH3, there's a lone pair on it. That lone pair counts as a steric group. It pushes the bonds as far away from each other also as bonds push each other away. So this nitrogen here would be sp3 hybridized because that lone pair is just in an sp3 hybrid orbital. It's not bonding, but it's in an sp3 hybrid orbital. It's being pushed away from the other bonds as much as can be. If you have an oxygen, you have 2 lone pairs, one here and one here. And those 2 lone pairs are both in sp3 hybridized orbitals. So lone pairs count for your steric number. They're just non-bonding electrons that are in hybrid orbitals as opposed to bonding electrons. All right, so if you have no lone pairs, right, that comes out to a tetrahedral shape, right, tetrahedral electron arrangement. All of these have tetrahedral electron arrangements, but the molecular geometry, which doesn't take into account the lone pairs, will be trigonal pyramidal, right, for nitrogen. So that's, here's my 3-membered pyramid, and that's all trigonal pyramidal is saying, 3-membered pyramid. And then bent for oxygen, which has 2 lone pairs. And if you think about it, right, you always draw water as a bent molecule. And the reason why is because you're just not showing the lone pairs. They're there, but this is an sp3 hybridized molecule, and those 2 hydrogens should have a roughly 109.5 degree bond angle. We'll see an example of that in a minute. If you have sp3 hybridization, you're usually going to have a trigonal planar arrangement of electron pairs, right? And that's where now you have your central atom, actually, let me go down here, central atom, and you have 3 electron pairs 120 degrees from each other. Trigonal planar, it's flat. All 3 of those electron pairs are 120 degrees from each other. Once again, it doesn't matter if they're lone pairs or bonds, they're still going to repel each other. They're still electrons, so you're going to get that 120 degree bond angle. They're going to push each other as far away from each other as possible. That's sp3 hybridization. Trigonal planar meaning 3 trigonal, 3 planar. 3 in as far away from each other as possible. This is boron. Boron does this very, very neatly, right? Because boron has 3 bonds and an empty p orbital, but we'll talk about that in a bit. And then oxygen can do this as well. If you have one of those lone pairs in a p orbital, you can get oxygen to be trigonal planar, and then carbon as well, right? Carbon, as soon as you make a carbon that has a double bond, right, and it's sp2 hybridized, now you get a 120-degree bond angle between the bonds. All right, and then linear arises from the situation where you have two groups, two steric numbers. Those two electron groups are going to push each other as far away from each other as possible, and that's going to get you this linear arrangement where they're 180 degrees from each other around that central atom. Okay, so we've pretty much gone through these already, but let's just define these in a more concrete way. All right, a sigma bond is head-on overlap. This is usually, in the case of organic chemistry, involving hybrid sp orbitals. So usually head-on overlap of hybrid orbitals if it's a carbon. So hydrogen just has an s orbital. It doesn't have a hybrid because it doesn't have access to that second shell. So hydrogen is just s orbital. But if it's a carbon, right, it's usually some sp hybrid. Some sp hybrid. And then, bonded to a hydrogen, right? So they're sharing an electron between a hydrogen's electron in an s orbital and a carbon's electron in an sp hybrid, be it sp, sp2, or sp3. So these are sp2, sp3, sp, and also s, right, for the hydrogen. And then pi bonds are going to be that side-by-side overlap of p orbitals, right? And this is key, right? This is only occurring with p orbitals. So around two bonds that already have a sigma bond between them, the pi bond is that side-by-side overlap. So they already have the sigma bond, and then that side-by-side overlap of the two p orbitals is what makes the pi bond. So with all of that hybridization comes just a little bit of interesting characteristic of these bonds that we can talk about. All right. If you look at the bond lengths in ethane, ethene, and ethyne, or ethylene and acetylene are the double and triple bond versions of ethane. These are just carbon bonded to carbon, right? The central bond is what we're looking at, the bond between the two carbons. If you look at the bond lengths, you'll see that as you increase the number of bonds between the two carbons, the bond length gets a little bit shorter. And part of that is because the attraction between the two atoms is stronger. The two carbons have more bonds between each other. They're held together more tightly in some. But another part of that is because the sp hybrids that make up those orbitals contain more and more s character. So remember, s orbitals are closer to the nucleus because they're spherical shaped, and p orbitals, right? P orbitals are further away from the nucleus, or they have more of their density further away from the nucleus. So here's our p orbital, right? And here's our s orbital. S orbitals are closer to the nucleus. And that means that the more s character an orbital has, the closer to the nucleus it's going to be. So this bond is composed of sp3 overlap, sp3 on this carbon, sp3 on this carbon, and I'm not drawing the back lobes, I should. This bond is sp2 sp2 and pp overlap. So one sp2 sp2 bond, right, which is like this, and then one pp overlap. And then this one is sp plus pp overlap plus pp overlap. So this is the sigma, right, and two pi bonds making up the triple bond, right, and this is the sigma, and one pi bond, right, and this is just a sigma. And the sp orbitals have the greatest s characters, so they're the ones that look the most like an s orbital, and therefore the ones where the electrons in them are closest to the nucleus because they have more s character. They got 50% s and 50% p, whereas this guy over here has 25% s and 75% p. So the more s character you have, the closer to the nucleus you are, the shorter of a bond you're going to have. All right, this last question down on the bottom, which would be stronger, a pi bond or a sigma bond, and why? I love this question. It's a great question. The answer is a sigma bond, and it's a sigma bond because it's that head-on overlap. So if I draw sp hybridized overlap, right, this is pretty straightforward, right? You got head-on overlap of orbitals. Every time I draw pi bonds, which is side-by-side overlap of p orbitals, I end up having to fill this in, right? And I don't do a good job. I'm a terrible artist. But I'm trying to show the side-by-side overlap, and it's not pretty. Well, head-on overlap is a lot more direct, and there's a lot more overlap between the head-on orbitals of a sigma bond, and a lot less orbital overlap between the side-by-side overlap of the pi bond. So the sigma bond is going to be the stronger one because it's a stronger overlap, greater overlap. And the pi bond is the weaker one because it's a less overlap. All right, so this is going back to that previous slide on shape, and I'm showing you now CH4, NH3, and H2O. And the geometry of these guys, the molecular geometry is very different. But the electron geometry, the arrangement of the electron pairs, right, is tetrahedral for all of these. These are all sp3 hybridized. sp3, sp3, sp3. So the electron geometry is identical for each one of these central atoms, right? It's just that in the case of nitrogen and oxygen, some of those sp3 hybrid orbitals aren't used in bonds. They're used in non-bonding lone pairs. So this sp3 hybridized nitrogen has one sp3 hybrid orbital holding a lone pair and three sp3 hybridized orbitals being used in bonds to hydrogens, right? And this one is 2 and 2, right? 2 lone pairs and 2 bonds. And that means that even though they have the same arrangement of electron pairs, right, same tetrahedral 109.5 degree arrangement of electron pairs, they have slightly different geometries. So we have names for these geometries, and that's what we went over on the last slide, or that slide where we were showing the shapes. This one we call tetrahedral, right, and this is tetrahedral. This is trigonal pyramidal, and this is bent. But I want to point out here that there is also a slight difference between the bond angles. If you look at the bond angles in methane, it's 109.5. As you increase the number of lone pairs, it becomes a little bit lower, 107 and 105 for water. And the trick to this is lone pairs have a greater repulsive force than bonds do because bonds are distributed over a longer area. There's another nucleus pulling those electrons a little bit further away. And lone pairs are solely focused around that single nucleus, right? So they have a greater repulsive force because they've got just a little bit more electron density in a smaller space. So what that means is lone pairs repel other electron groups a little bit harder. And these numbers just get a little bit smaller for the angles between the bonds because they're being pushed by that lone pair further away from the lone pair, right? Further away from the lone pair, but a little bit closer to the other bonds. So once you get to the point where it's oxygen and those 2 lone pairs are repelling each other and the bonds, right, that number gets all the way down to 105. Still really close. If I ask this type of a question on an exam, I'm not looking for exact numbers here. I'm looking for the fact that you recognize that oxygen should have a number closer to 109.5, right, a bond angle number closer to 109.5 than 90 or 180, right? I'm looking for general numbers here that get you in the right vicinity. Right? I'm not going to ask you for exact numbers here, so don't worry too much about that. All right, so here's some hybridization practice. And there are lots of ways to go about looking at this. I think that for each hybridized atom, what I like to do is count the number of pi bonds, and that tells me how many p orbitals had to be reserved from that atom. So what I'm going to do is I will post this slide. I will post the answer to this slide on my courses. And you guys can check your answers against this, but go ahead and give this a try. If you get something that's different than what I get, that's okay. I'm just going to post this slide. Feel free to contact me, send me an email, or talk to me in my office hours, whatever you got to do. I will gladly explain it. But I'm just going to post this as an answer key in my courses filled in lecture note practice problem area. Same thing with this one. This one's asking you to draw Lewis structures, right? Describe the orbitals used in each one. So that's the hybridization, and then showing the orbitals used in each bond and indicating the approximate bond angles. All right, so I promised I would come back to methyl cation, and I think I said I would come back to boron, but they're both the same, and we're going to see why in a little bit. But this one is a different scenario in terms of hybridization. Something different is going on here. So if you look at methyl cation has 3 bonds, and it does not have a complete octet. So here, instead of having sp3 hybridized orbitals and having an empty sp3 hybrid orbital, which would give me 109.5 degree bond angles, if I make that empty orbital a p orbital, so that orbital that doesn't have any electrons in it, a p orbital, I can get these remaining hydrogen bonds, CH bonds, up to 120 degrees apart. So I can get a few extra degrees right between electron groups by leaving that empty orbital as a p orbital. Now, this makes sense in a couple of different ways. Number one, in a VSEPR way, it makes sense because by leaving it as a p orbital, we don't care that there's a 90-degree angle between the CH bond and the empty p orbital because there's no electrons in the empty p orbital to repel. So that bond angle doesn't matter. That angle between the CH bond and the empty p orbital doesn't matter. There's no electrons there to repel. But we can get the extra 120 degree, the extra few degrees by going to sp2 hybridization around that central atom. Now, in an electron energy way, it does make sense because if you have sp2 hybrids, sp2 and 1p orbital, these sp2 hybrids are lower in energy than sp3 hybrids would be. And it's not much, but it's enough that it makes a difference. So putting those electrons in sp2 hybrid orbitals, because they have more s character, because they're closer to the nucleus, they're lower in energy, they're more stable than sp3 hybrids are. So by moving those electrons into sp2 hybrids and leaving an empty p orbital, you get a little bit of stabilization around that carbon atom. So methyl cation with an empty p orbital is going to adopt an sp2 hybridization. sp2 hybridization. It's going to be trigonoplanar, which I have shown here. And here's my electrostatic potential map, which shows that there's just a deficiency of electrons. Methyl radical. This is the case where you have a carbon with, once again, an incomplete octet. So I'm going to draw the Lewis structure here. Technically, this carbon is neutral, right? It's neutral because it has, if you do the formal charge calculation, right? Well, don't do that yet. If you do the formal charge calculation, carbon normally has 4 minus 1 non-bonding electron. That's the radical electron there, the single electron, minus 1/2 of the 6 bonded electrons, which is equal to 0. Right? So it's a neutral formal charge. But this is also an electron deficient situation. So this is also, methyl radical is also going to be sp2 hybridized. And right now that's not particularly important, but when we get to radical chemistry, this is going to be very important. So these carbon-hydrogen bonds are going to be composed of sp2 hybrids because radicals behave like cations. They are electron deficient. They're missing that second electron there. So because they're electron deficient, they're going to behave like cations, and methyl radical is going to adopt sp2 hybridization in order to get the maximum stabilization out of it. But methyl anion is different. Now you have a carbon with a lone pair. This is electronically identical to ammonia, except that ammonia is neutral and methyl anion has a negative charge. So ammonia is neutral, but it looks identical, right? Because it's 3 bonds, 1 lone pair, 3 bonds, 1 lone pair. Carbon just has 1 less proton than ammonia, or than nitrogen, so therefore the carbon with 1 lone pair has a negative charge. So methyl anion is going to behave just like nitrogen would. It's going to adopt that tetrahedral electron configuration, trigonopyramidal molecular configuration, right, as shown here. Electrostatic potential map is going to show that there's a lot of electron density above the molecule, and that's indicating that the anion is in an sp2 hybrid orbital that is focused on one side of the molecule, or an sp3 hybridized orbital focused on one side of the molecule. So 4 electron groups, behaves like ammonia, behaves like anything else with 4 electron groups. It's going to be sp3 hybridized.